a coupling library in contrast to a coupling framework. So the other hand would be the ESMF from the US. And coupling library is linked to your component, your icon or whatever model you have. And the model calls the coupler. While on the other hand, a framework, you run the coupler and the coupler calls your model. That's the difference, just in case you're interested. YAC itself is written in C, but we have a C, Fortran, and Python interface. Basic features are the coupling of 2D fields on the sphere. We support all commonly used grids, regional, global and regional grids. We support any decomposition. They do not have to match between the components you want to couple. And we have a very strong parallel online weight computation, meaning you do not have to provide any weight files. So during the initialization, we will compute everything that is needed for the coupling. And you just need to configure in a small text file what you actually want to do, and everything else will be done online and will have no significant impact on the overall runtime normally. Yeah, originally it was started by a colleague from the Max Planck Institute, René Redler, and myself as a project. And now it is primarily developed at DKRZ. We started in 2011, 2014, we had the first first major release. And I think from then on, it was also used in Icon. And it is developed independent of Icon, but Icon is the main user. So it is not specifically written for Icon, but it works quite well there. 2021, I did a complete rewrite of the internal parallelization scheme, which resulted in version 2, and version 3 was in a rewrite of the interface. New configuration file looks much leaner now, and currently we are at version 3.8, and 4 is hopefully coming this year or next year. Regarding interpolation, we have a lot of different interpolation capabilities, from conservative first order, second order, nearest neighbor, linear, polynomial, RBF, creep fill, explicitly runoff mapping. So there's a lot of different methods and a lot of configuration options. I have a link here where you can look up everything that is available. And YAC also introduced the stack concept, or interpolation stack concept, meaning certain interpolation methods may fail when trying to interpolate a target point, because due to constraints too far away or whatever. And usually what you have is then a fixed fallback method. You may say, I want to do nearest neighbor or something else fixed. And with YAC, we came up with the idea that we do not provide a fixed fallback, but you can define a list of interpolation methods. And when you start interpolating your target points, they will be assigned to the first method, and every target point that fails will be passed on to the next method, and so on. And you're completely free on defining the stack. And yeah, that makes it really flexible. And there are, for example, methods like the fixed method, which just assigns all remaining target points a fixed value. And that way you can make sure that every target point gets interpolated. Just a few basic links where we have a public GitLab repository and we have a Doxygen documentation page. This is not just simple, automatically generated, all functions listed, but we have a lot of additional pages there that describe everything in detail with examples, pictures, a lot of text. Yeah, if anything is missing, anything is not, you don't or it's not clear enough, just contact me, I will take care of that. In case you need support with coupling, with using YAC, not in general, please. You can set up issues in the GitLab repository or contact me directly via the mail, or if you're in the MetaMost channel of Icon, then you can contact me at K202077. That's my username there. So just a couple of basic concepts. The first and most basic concept is the instance. Usually you have one instance of YAC and everything else is assigned to it. And it is associated with a communicator, usually MPI World. And one instance contains all processes that want to couple. You can have multiple instances if you have different groups that are completely independent. And usually YAC will define a default instance, but in case of icon, it generates its own specific instance and you always have to reference it. When generating an instance, you have to provide a communicator that contains all processes that are assigned to or associated with this instance. Usually they're this MPICOM world. But if the splitting of MPICOM world is a little bit more complex, for example, if your setup also contains common plugin processes that do not want to couple, then you have to do it by hand using the MPI handshake algorithm that we developed together with DWD for this purpose. And there you have to generate the communicator yourself and provide it to the instance constructor. Once you have your instance, each process can inform YAC which component it belongs to. For example, a process belongs to atmosphere or ocean. And this basically is a subgroup of processes that define fields altogether. And a process can be part of more than one component. For example, you could have a atmosphere component and an output component on the same process. Then we have grids. This is basically just your vertices and cell connectivity. But with YAC, each process only defines its local part of its grid, and no process sees at any point the overall global grid, because for very high resolution grids, there would be an issue with memory. You can have more than one grid on a process. For example, your global part of the grid, and if you have nesting, you can have a part of your nest, for example. Grids can be shared by multiple components, and you can help YAC a little bit if you have global IDs for each vertex, cell, and edge that explicitly define each unique point globally. So a vertex with a certain coordinate that is on multiple processes, for example, should then get the same global ID. That way, YAC is able to identify these across processes. I can generate them internally, but afterwards, then you can't use wait files anymore. And that takes a little bit of time. So I can provide these automatically, so nothing for you to worry about. Masking, we have different masks. There are two basic masks. One is a core mask that helps you deactivate duplicated or degenerated cells. Degenerated cells occur in special grids where you have cells that are completely distorted and intersect with each other. These can cause problems internally. If they're too big, then certain algorithms might fail, and you can deactivate them completely if you know they will not contain any valid data. Duplicated cells can occur if you have, for example, a regular grid that goes around your pole, and then at the ends it overlaps with each other. Then you can have duplicated vertices, and you can deactivate them to avoid internal issues. In Icon, the core mask is used to deactivate the local halo cells because it is assumed they do not contain valid data anyway. In addition to the core mask, you can have a field mask. So for example, the atmosphere component contains a land, and the land fields are only obviously defined over land. So you can mask out, for example, the ocean cells. And while the core mask is defined per grid, the field mask can be defined per field or used by multiple fields. Then you have the so-called points. These are the coordinates and the location of the coordinates, in this case, usually vertex, cell, or edge, at which a field is defined. In Icon, these are usually the cell centers. You have to provide the coordinates of the cell centers and tell YAC these centers are the centers of cells. And once you define a field, you provide then the points at which the field will be defined, so at the cell centers. And a field is basically represents a data field from Icon, like sea surface temperature. And in order to define a field, you have to associate it with a grid, potentially a field mask, and a set of points. Then, as mentioned before, actually YAC only supports the coupling of 2D fields on the sphere, but oftentimes you have 100 levels or 50 levels, and you don't want to define a field for each of these levels. So you can set a collection size to the number of levels, and each level will then be interpolated independently of each other. So we only have horizontal interpolation, but no vertical interpolation. Another application of the so-called collection size are if you have a number of categories that are sent using the same interpolation method. And in case of ICANN, for example, there's the ocean sea ice bundle, which contains three 2D fields, the ice thickness, snow thickness, and ice concentration. And in this case, you would use a collection size of 3 and send them at once. Then we have the concept of interpolation, obviously. And interpolation is basically only a distributed matrix vector multiplication, where your source field is the source vector, your target field is a target vector, and in between you have the weight matrix, which is sparsely populated, but the multiplication of the source vector with the weight matrix gives you the target data. And distributed meaning the source vector and the target vector can be distributed in any way across the processes. And YAC will take care that the multiplication with the weight matrix is done as efficiently as possible in parallel across all processes. You can wait. Yeah.
Just as an add-on, we will use that in the exercise, that we will have a distributed icon grid, and the target vector will just be on one single task. So this is, we will see this in action right afterwards.
Cool. So when using YAC, you do not have to worry about the composition. This is done automatically. You can write out weight files if you want to use them in other applications, or want to investigate how certain target points are interpolated. You can write them to file, and this file will then contain the global weight matrix. And as the last concept, we have a couple. A couple basically tells YAC, I have a source field and a target field. Please interpolate them at a certain coupling period. Define if the source component provides data more often than the actual coupling period is, then what YAC is supposed to do with the data in between. So you can compute an average, sum it up, or just use the last available data. A source field is defined by any field is defined by the name of the component, the grid, and the field, because a field could be defined on multiple grids, and then these are different fields. That's why we need all 3 names. Then we have the lag, meaning, for example, I can always does its coupling at the end of the time step. So when a model starts at 0 hours, then I can compute for, let's say, a time step of 1 hour. Then the first available data is actually at 1 o'clock. So not at the start of the 1, but delayed by 1 time step. In this case, that's why for ICANN, the lag is always 1, because you do not provide the data at the start of the 1, but after the first time step. And yeah, and obviously when you define a couple, you have to define the interpolation stack, and there are a couple of other options like scaling, or scaling could be used if you want to change units from Kelvin to Celsius or whatever. There are some more options, but that's too much for today. How do you use it? So you start by initializing YAC. This is the generation of the instance, usually involves the splitting of MP-icon world. Then you have a couple of local configurations where each process defines which component belongs to what part of the grids, or which grid and what part of the grid it has, defines its mask and its fields. This is done via the user interface. And then there are a couple of global configurations. These can be defined via the user interface or a configuration file. And this can be done by any number of processes, could be 1 or all, or a selected number, that doesn't really matter. This data includes the definition of the calendar, the start and the end date of a run, which fields are supposed to be coupled, and a couple of debugging options. Once all definitions are finished, you have a collective call where these definitions are synchronized between all processes. In case of grids and masks, only the names and where they are defined is synchronized and not the actual vertices and data, so just metadata. And based on this information, YAC will then internally generate the weight matrices and communication patterns for executing these interpolations. Afterwards, you can go into your usual time loop, and where YAC provides a asynchronous put operation for sending data and a blocking get operations for receiving data. And we also have an asynchronous get operation combined with a wait, but it's just for playing around. Once you finish with your time loop, we have a finalization for cleaning up everything. I have here 2 additional links for a overview with how to use or with all these steps with the associated calls, and for the C, Fortran and Python interface next to each other, so we can compare them with a lot of text to describe all these steps. And we have a interface reference page where all interfaces that are available listed, and you can easily search for them. As I mentioned before, we have a configuration file which defines the global configuration. You can read in an arbitrary number of different configuration files, and these can be read in by any process. A single one, all of them, doesn't matter since we synchronize the different definitions afterwards anyway. Usually when you write a configuration file, you would use the YAML format. We fully support YAML version 1.2, which is quite interesting. Has a lot of nice features, which you come to later. You could also use alternatively the JSON format. So why do you need a configuration file if you can do it via the user interface? Because you may want to change your configuration, change the interpolation, change the coupling period or something else. And in order to not requiring to recompile, you can easily just change a couple of lines in the configuration file, which makes it rather easy. In Icon, this configuration file is automatically generated in the run script for each run. And that's why in the run script, you can set up your coupling configuration easily. Just as a side note, in case you write a tool based on YAC and you need an interpolation, so the user interface for generating interpolation stacks is rather complex, but you have the option to provide a string, which is basically the same that you also provide in the configuration file. And from this string, YAC can generate then the interpolation stack. So you could provide the tool which accepts as an argument the complete interpolation stack configuration. And this is usually better done in JSON. That's why I'm mentioning here from string JSON. Just for playing around. And here's a link on all the parameters and options you have in the YAML file. Oops, no, I was one too far. So here's an example of a configuration file, which I've taken from an Icon Run script. This is for the coupling of the Icon atmosphere with Icon wave. And on the left-hand side, this is a part that is initially ignored by YAC because these are no, so for example, the component, interpolation stack and stuff. These are not keys that are interpreted by YAC, but you define a couple of things which are used again later on. So you define what you mean by atmosphere. This is a component called Atmo, a grid called Icon atmosphere. These are the internal names provided to the definition routines for defining grids and components. You have a wave component, then you define what you mean by atmosphere to wave coupling. Say wave is atmosphere. This star means basically it's an include of something that was defined before. That's what this is a feature of the YAML format. You define, I have a time rejection of none. So even if you have more puts than actual gets, then you only take the last data. You could also use average or sum or something like this. Then you define what is wave to atmosphere. Oh yeah, I mentioned before. Icon always has a lag of 1 because it provides the data after the first time step. And then we define here an interpolation stack. It starts with a polynomial interpolation followed by a nearest neighbor. And if anything else is left, it will get assigned a value of minus 999.9. And then the actual part that is read by YAC is here. You define at first what time format you're using. In this case, ISO format. We also have hour, minutes, days, whatever. You define the calendar. This is important because otherwise I wouldn't know how to interpret certain time formats, like what is a month. And then you define what you actually want to couple. And again, we have a little YAML syntax. This is basically a merge. And you provide a list of things you want to merge into your current section. And so here we merge in that we want to couple atmosphere to wave. We define the stack that we are using. We define the coupling period. And since this whole script is, or this whole conversion file is generated by the ICANN1 script, we have access to the variables of the ICANN1 script. That's why coupling period is a variable from the run script. And then we define a list of fields to which this configuration applies. And again, for the other direction, in this case, wave to atmosphere, and we only provide the roughness length, whatever that is. Yeah, you might notice start and end date are not mentioned here because they are defined by ICANN through the user interface. Yeah, I was asked to give a little example of how a program using coupling might look like. So I wrote two programs. On the left-hand side, we have a generator which provides a noise field. And on the right-hand side, we have a plotter that receives the noise field and then plots it to a PNG file. And these are two Python programs which are fully functional. And I later provide the link to the repository where you can test it. So for the generator, we start with a couple of imports. We define the calendar. We generate an instance. We define the time interval at which we want to do the coupling. So start date, end date. We define this. These two programs are only run only on a single rank, so they are not parallelized. But in parallel, it wouldn't look much different. We define the left program as part of the generator component. Then we use a little bit of NumPy to generate an X and Y axis. The X axis goes from half pi to 1.5 pi, and the Y axis goes from minus pi quarter to a quarter of pi. And these two axes are then used to generate a regular 2D grid, which basically covers 1/4 of the globe. And we also have constructors for unstructured grids where we require different arguments like explicit connectivity. But in this case, the two axes and X and Y are sufficient, and YAC will automatically infer all the vertex coordinates and the connectivity between the cells because it's obvious in this case. Then we define the points. We define they are located at the corners of the grid, and that's why we only have to provide the two axes again. We only have a collection set of one. We define a field called noise field, set the component points, collection size, and tell YAC that we are going to call put every 3 hours. Once all of our definitions are finished, we call the instance endDef, which basically means I'm finished. Please wait until all interpolations are generated. And then it's a simplified time loop, which just waits until the field, so the current date, so the date time of the field is initialized with the start date of the run. And which each puts the internal timer of the field gets increased by the coupling by the field time step, which is 3 hours in this case. And we are waiting until the field reaches the end of the run. And until then, we will call one put after the other with a randomly generated field. And on the other hand, we have the plotter, very similar, imports calendar, instance, component, this time the plotter, a similar grid, but this time a global grid going from 0 to 2 pi in the x-axis and minus p half to p half in the y-axis. And so meaning we have a global regular grid. And in this case, we define we generate a cell center axis and tell YAC that our points are located at the cell centers. Yeah, again, we define a field. In this case, we even use the same name as the other side. We could use a different name, but that would have to be reflected in the configuration file. And in this case, the plotter will plot, or we call the get every 6 hours. And afterwards, we read in a configuration file, because here we haven't defined any coupling yet. So we are going to read in this from an external file. Again, we have the NTEF, and this is a synchronization point between the two processes, and it will automatically generate the interpolation. Again, we have a simplified time loop, and here we call a get, where we will receive the data, and the remaining part is just taking the received data and plotting it to a PNG file. This is what the configuration time looks like. We have a time unit of an hour. We have a single couple, the source component being the generator, source grid, generator grid, and so on. Field name is noise. We want to couple it every 6 hours. The interpolation is an average interpolation, basically a linear interpolation, and followed by a fixed interpolation that assigns a user value of -1 to all remaining points. In order to execute this, you first have to set the Python path to the Python directory in the YAC build directory, and you can then call it as a simple npmd program with mpi run -n1 Python 3 generator pi and so on, and this is the output you get. You might notice there are a lot more generating noise than plotting noise, because the generator has a coupling field frequency, field time step of 3 hours, while the generator only has a field time step of 6 hours. That's the reason for that. The resulting pictures look something like this. And as I mentioned before, the generator only had a grid that covered 1/4 of the globe. That's why this is the field that was received from the generator, and everything else, or the remaining target points, received the fallback value of -1 from the interpolation stack. If you want to check out the example, that's simply here. And this repository, which should be public, I think. This plotter script could also be easily adapted to be run together with an icon run, and you can simply attach it to any icon run and plot out any field that you want. That works quite nicely. Yeah.
Yeah, actually on the last point, at the moment this is relatively new to me, so I don't really see the connection to how you would, what you would change to use it with icon, for example. You maybe.
Yeah, that's. You would in the script, you would have to adjust the field time step to something that's useful to you. So in this case, it would plot every 6 hours. You would have to adjust that to the time you want to generate pictures. And then here you would have to adjust the source component, for example, Atmos and icon Atmos grid. And the field is probably called differently in icon. Then you can use field and then to the submap calling source name, the name on that icon uses, and target the name that your plotter uses. And that's it.
But just one question. Are you all familiar with this MPI run call structure on the right? This where you call two different binaries or the same binary in two different modes. So that's the essential part, which is here in your example without icon, but usually there is icon in two flavors. Like the first one is not generator pi, it would be the icon atmosphere maybe, and the second one would be the ocean. So for those who have not so much experience with MPI and MPI run, this might seem to be unfamiliar, but that's the essential point of running a coupled executable.
Yeah, so maybe following up from that, in the end, probably
this would be synchronized between icon and.
Yeah, right. So let time synchronize because these two do not seem to be synchronized.
You have multiple synchronization points. One is the instance definition because it contains a splitting of MPI icon world. Then you have the component definition because I need that in order, if you ask afterwards, can I have a MPI communicator between component A and B? That's why I have a synchronization point there as well. And then you have an indef, which is a synchronization point in order to be able to exchange definitions and compute all the interpolation weights. And then the put and the get are not directly synchronization because the put call is asynchronous. So the source component can call put as much as you want, and it doesn't have to wait for the receiving part.
Oh.
That's an asynchronous send.
Okay, but if you want to use YAC to modify fields, which would then go back into icon.
That's a two-way coupling. So you, for example, you have a put to a component which receives something, and at the same time, the other component may also call a put, and icon may receive internally. That's what I mean.
Yeah.
So exchanging of fields. In that case, that is an implicit synchronization point. Yes.
Okay, but that would work, and then
That's what icon does. Yeah. You have to call. You should call the puts first and then the gets. Otherwise, you get a dead. So an icon usually it is like if it wants to, if the icon atmosphere wants to communicate with the icon ocean, you have all your puts and then all your gets, and yeah. But that obviously means that all the data you receive is one time step too old, because they don't run after each other, but in parallel all the time. So you always get the data from one time step before. Because let's say the atmosphere finished its first time step. It doesn't send the data to the ocean. The ocean computes its first time step and returns the result. But instead, ocean and atmosphere run its first time step instantly, exchange data, and then do. So that's why you're always one time step too late. For other models, this is different. For example, for the IFS NEMO that is used by the ECMWF, they run after each other. And then only one gets the old data and the other gets the data on time. Yeah, so now a little bit more on detail on how YAC is used in ICANN. ICANN is very special in how it is used in contrast to most other configurations because ICANN is SPMD, meaning you have a single program, multiple data. So you only start a single ICANN executable, and during the initialization, each process will decide, I'm ocean, I'm atmosphere, I'm wave. And then later on, will split into different components. While in other configurations, you have your IFS component or your IFS executable and your NEMO executable. So right from the start, each process knows what it's going to do later on. This is I don't know any other model that does stuff like this. Makes some things a little bit more difficult. But anyhow, just as an introduction. The first time YAC comes into play when running an ICANN run is right after your MPI init, because there at that point, ICANN needs its internal communicator. Originally, ICANN simply used MPI icon world, but when coupling came into play, that's not possible anymore. So you have, right after the initialization, you have a splitting of MPI icon world using the MPI handshake. And it splits the world communicator into an ICANN communicator containing all ICANN processes, not yet distinguishing between ocean, atmosphere, and wave, but just all ICANN processes. And if necessary, it will also, so this call will also generate a communicator for COM-IN and for YAC, containing all processes that that use COM-IN and one communicator containing all processes that want to use YAC, that might contain external components. Yeah. And then that's finished for now. And afterwards, ICANN goes into its initialization. And once each process is decided what it wants to do, this is basically, for example, in the construct atmosphere model routine. There it initializes then its YAC instance. And in the destruct atmo model, then you have the destructor of the instance. Once each component has or each icon process has decided what it wants to do, it reads in a couple of nameless files. And in one of these nameless files, you have the coupling mode NML, which contains flags like is coupled to ocean, is coupled to hydro disk. And in this case, this is from an atmosphere name list, and it was asked to be coupled to an icon ocean and to an external hydrology model. This is your basic, from a basic icon XPP setup. Yeah, and since you usually don't access the source name list, Mo coupling name list directly, there is also the source coupling configuration model, Mo coupling config F90. And there you have a couple of query routines where a process can ask, am I coupled to an external hydrology model? Am I coupled to an ocean? And so on. So this is then how later on it is decided what more needs to be built and whether YAC is supposed to be configured or not. So during the initialization of each component, at one point, if it is supposed to be coupled to something, it will call a constructor from a Mo X coupling frame, where X is atmosphere, ocean, or wave, meaning if an atmosphere model, an atmosphere process wants to couple, it will call the constructor from this file, and it will start by defining I am component atmosphere, I have the following grids, and I have the following cell centers. Afterwards, based on the query routines from before, it will then call the constructor of files or of modules looking like this, where X is something like atmosphere, IS, NWP, ocean, wave, and Y is something like atmosphere, ocean, wave, geo, hydrology, whatsoever. And this is basically for each specific coupling to another component, we will have an individual model. So you will have your Mo, Atmo, ocean coupling, meaning this is what the icon atmosphere uses to define its definitions required to do the coupling to the ocean. And on the other hand, you also have a Mo ocean atmosphere coupling, which is used by the ocean component to define the coupling with the atmosphere. And you might notice suddenly that you have Atmo, IS, NWP. That looks a little bit duplicated. The reason is you have two different atmospheres in icon, and sometimes parts work differently. So where do I get the fields from that I want to send or receive? And that's why all the parts that are identical between the two of them use the Atmo, and all the parts that are different between the two of them use either one of these.
Yeah, so just to mention, because we never encountered AES, I think, this week so far, we deal here with the NWP part, and the NWP implementation in AES is what Johan Jungklaus was, for example, referring to yesterday morning, the MPIM flavors of icon. So these are slightly different, and this is why we have this splitting.
Yeah,
This is still currently developed.
AES, I would have done, yeah, it's still under development. I thought some of the parts are even ported to C++ right now. So, no, yeah, it's live and ticking.
but it's in development and in use.
But the wording is unknown, Mike, and this is why, yeah, AES needs to be explained.
Yeah, and the list for the Y is a little bit longer because this also contains external components like Clio, which is a droplet model, hydrology model, can be also something like a quite recently there's a simple Python script that reads in original ERA5 data, which is rather coarse, and provides it through YAC to the component. With the advantage that if you have a very high resolution icon run, what you usually would do is interpolate the ERA5 data to your grid, to the high resolution icon grid, producing a lot of data and reading that indirectly. And the alternative is to have a simple Python process reading the original data and then doing the interpolation through YAC online and simplifying the reading. But anyway, yeah, so there are a lot of different components here. And in addition to the constructor and destructor, these files usually also contain something like couple wave to icon. Names might look a little bit different, but are rather readable, meaning this is from the wave Atmo coupling F90, and this is called in your time loop when the wave wants to communicate with the atmosphere. In addition to these two files, you have the Mo coupling utils. This is because the YAC calls are not specifically written for icon, so they are rather general, and oftentimes a lot of the arguments are trivially or are repeated in the icon runs. So we have a simplification layer around the actual YAC calls, and that's why in the files above you will usually only call couple underscore routines, which are a simplified version of the actual YAC routines. And in this source coupling directory, you might also find, if you look closely, a more output coupling. This is a very specialized coupling available in the atmosphere, and this takes all the fields that are in your internal var list and basically registers them in icon, and any component that wants to run with icon or runs alongside icon can access these variables. And this is how your plotter script can access internal variables of icon, because all internal variables are automatically available via YAC through this output coupling. And if you have, for example, if you want to do any several output server implementations for icon, and that use different grids, because the icon grid is usually not so good for post-processing. So, for example, there is an output server using a HereFix grid, and that accesses the internal data via this output coupling. Just to have at least one picture. So you have your component driver, you have your time loop. The component driver will call the coupling frame constructor. The coupling frame constructor will call the respective XY coupling constructors. At some point during the time loop, it will call the coupling XYZ routines. And at the end of your run, it will call the destructors and so on. And all of these use the coupling utils to simplify the use of the coupler.